Welcome to your lesson on the laws of exponents, also called the laws of indices or index laws. This is a big idea. It comes back over and over and over again in every mathematical thing you're going to do. There's an assumption you already have a good understanding of this. You've done some exponent laws before. Basically, to begin, this is called a power relationship. That's called the base. This is called the exponent or the index. And for example, 125 is 5 to the third power, means 5 to the third is the exponential form of the number 125. Okay, so 5 to the third means 3 factors of 5, or 5 times 5 times 5. Laws of exponents. Basic rule here then is if you have x to the nth power, you can write this as x times x times x times x all the way until you have n x's multiplied. For example, 5 to the third, as we said, is 5 times 5 times 5, because we see a 3 there. Okay, let's take some notes now that you've been provided with a page with lots of rules, and there's going to be examples added to that. First basic rule is when you have a base with the power m times another base, same base, different power, you add the powers or exponents. So add that to your rule, and here's 3 examples that are on there. So 2 to the third times 2 to the second will be 2 to the fifth because you add those exponents. X to the fifth times x to the seventh will be x to the 12th because you add those exponents. And this one here, a little bit more going on. You multiply the coefficients, -3 times 2 to make -6. Then a to the 8th power times this, you're going to add those exponents, and 8 plus -3 is actually 5. And then b, this is like a b to the first power, and b to the fourth. That means we have b to the first plus b to the fourth, and then we have b to the fifth there. All right, why does that work? Well, let's take a look. So this x squared times x to the fifth is actually 2x's here, because this is x times x. This is actually 5x's multiplied. And then if you take that and multiply it, you end up with having all 7x's all multiplied, and 7x's multiplied can be written as x to the seventh. So what that tells us is when you see these exponents, you're just going to add them and make that because of the multiplication that takes place behind the scenes. All right, next rule. When you have parentheses and exponents on the outside, the exponent is applied to both pieces, like this. First example, second example. So here we have 7x to the fifth power. This is not going to be 7 times x to the fifth. It's going to be 7 to the fifth times x to the fifth, because that 5 is applied to both of these. And 7 to the fifth power is 16,807, and we have x to the fifth. Over here, we have 3 pieces inside, so that 3 goes on all 3. It goes on the 6, the x, and the y. So that exponent, 6 to the third power, is 216, and then x to the third, y to the third. Next one, when we have, same thing, an exponent on the outside of a parenthesis, but also if we have an exponent on the inside, you're going to multiply those 2 exponents. So we have m times n, not add, but multiply. So if we have this, we're not going to have 3 to the 6th power. We don't add these, we actually multiply them. So we do 3, and it's 2 times 4 to the 8th power. Over here, it's going to be 5 times -7, so we have x to the -35th power. Same rule, now we have multiple things on the inside, so as you can guess, that exponent p will be applied to both of these, so multiply here and multiply here. Here's an example of that. We have 3y to the third power. That 4 is applied to this. There's a 1 there that we don't see, 3 to the first power, so it ends up being 3 to the fourth, and these 2 are multiplied, y to the 12th. 3 to the fourth is 81, and y 12th. Over here, that 2 multiplies that exponent, becomes 2 to the 6th. That 2 multiplies that exponent, 8 to the 4th, and that 2 multiplies on the exponent here, which is actually a 1, and we get b to the 2nd. 2 to the 6th power is 64, and then we have that. All right, this is a pretty straightforward property. Anything to the first power is just itself. So 5 to the first is 5. X to the first is x. All of this in parentheses to the first power is all of that, unchanged. Next, division. All right, this is another major or important law of exponents. When you have division, it's actually going to be with the same base. It will be the top exponent minus the bottom exponent. Subtraction occurs. For example, if you had x to the 12th over x to the 5th, that would be equal to x to the 12 minus 5, and that is 7. Another way to look at this is, where do you have more x's? Here, if you wrote this out in expanded form, it would be 12x's multiplied. Here would be 5x's multiplied. On the top, we have 7 extra x's multiplied. So that's why we have x to the 7th as our answer there. Here's another example for this one. A little bit more going on in this expression. First, we'll reduce 20 over 8. 20 over 8 reduces to 5 over 2 if I divide both of these by 4. Then the rule about subtracting, you have 8 to the 9th here, 8 to the 5th, so I do 9 minus 5. And b is 3 and 7, so I do b to the power 3 minus 7. That simplifies to 5a to the 4th, a to the 4th from there, and this is a negative right here. It's important to know that when you have negative exponents and you have a fraction, this negative here, notice how it's been dropped to the bottom and became positive. Remember that rule. All right, and the reason for that is, if you look at here, again, if you think of it in terms of where do you have more a's, you have 4 extra a's on top here, so there's a to the 4th in the final reduced form. But here, when you look at the b's, there's only 3 b's on top, but 7 b's on the bottom. There's more b's on the bottom. There's 4 more b's on the bottom, so there's our b to the 4th on the bottom. So why does that work? By the way, anytime it said this y slide on the back of your page, there's some notes where you have this example and you can express why this happens. So go to the back side and write this in. Here's an example of why this works. That expands to 5x's multiplied. This expands to 3x's multiplied. Then if we do some cancellation of x's, cancel, cancel, and cancel, we're left with 2x's on top. So that's like an x squared. So that tells us why that rule exists. When you have that, why we do that? Why we subtract the two exponents? Because of this cancellation that occurs. And that subtraction there gives us that. Same answer. That's the reason right here behind this rule. All right, so try these. Pause the video and in your notebook, get to a new page in your notebook and try these ones here. They should not feel too bad. These should be pretty basic. See if you can simplify all those. All right, check your answers. See how you did. All of them will pop up here. Here's the first 6. Pause the video if you need to. And here's the last ones there. Okay, hope you did well with those. Let's look at a couple more properties. If you have division and the m on the outside, or an exponent on the outside, that exponent applies to all the pieces on the inside, just like with multiplication. So here's an example. We have 2 on the outside here. That 2 will apply to every piece. It will apply to the 3, the x, the 4, the x here, and the y here. So if that happens, let's take a look. This squared goes on the 3, and 3 squared is 9, so there's 9. That 2 multiplies this exponent here, and we get x to the 6th. That 2 applies to the 4, so we have 4 squared, which is 16. That 2 multiplies this exponent, x to the 4th, and that 2 multiplies this exponent, y to the 10th. That can be reduced. Notice we have 6 x's on top, 4 x's on the bottom. There's 2 extra x's on the top, so x squared. After you cancel those, we have an x squared on top. There's the full reduced form. All right, so you're ready to try some more in your notebook. Pause the video once all these appear and give those a try. You can do it. Okay, check your work. There's the first 6. Hope that went well for you. Pause it if you need to check something out. And here's the next few. Okay, hope it all worked out. Let's look at just a couple more things. So another rule is when you have any base to the exponent 0, that's always going to equal 1. So 18 to the 0 is going to be 1. Y to the 3rd with that 0 power there, it's going to be 1. All of this to the 0 power is going to be 1. Always 1 when you have the 0 power. Why does this occur? So on the back again, you'll have this example of y. You have these here, x to the 4th over x to the 4th. As we know, that expands to that and that. Every single one of those pairs of x's will cancel, and we would just be left with 1 over 1. and that's 1. Now let's look at this a different way. What if you used our rule about subtraction? All right, so that ends up being this because we subtract those exponents when there's division. 4 minus 4 is 0, so we have x to the 0. And that tells us that x to the 0 must be 1 because we began with the same thing over here. When we did this process, we got 1. When we did this process, we got this. So those two things must be equal. All right, another rule, when you have a negative exponent, it equals 1 over that value there. This is a really important one. It comes up often. So for example, if we have 6 to the negative 2, I see a negative 2 power on that 6. So notice by this rule, this 6 can drop to the bottom of this fraction and then that exponent becomes positive. So very important rule. Remember that. This, again, can drop to the bottom. And if this moves to the bottom, we're only left with 1 on the top. And there's 6 squared on the bottom. That simplifies to 1 over 180, because 6 squared is 36 times 5 is 180. Here's another example. So here we have this fraction and this exponent out here. That exponent I'm going to apply to the 3 and the 4. So that exponent goes on the 3 and the 4. Now I see a negative exponent here and here. This rule, you have to know, works backwards as well. So this 3 to the negative third is going to go to the bottom of the fraction, whereas this 4 to the negative third is going to come to the top of the fraction. So basically we're just flipping those. Notice what happened here. So that 4 went up, this 3 went down, and both of them now have a positive exponent. Why does that work? Let's take a look. So here's one that has a cube on top and a 5th power on the bottom. So 3x is there, 5x is there. If I cancel away pairs, I'm left with 2x's on the bottom. So this is the same as having 1 over x times x, which is 1 over x squared. And let's look at a different way now. Now the rule about subtracting. So the rule about subtracting tells us we take the top exponent minus the bottom one, 3 minus 5, which is x to negative 2. And again, we started with the same thing. This thing here, this thing here. This approach got us to this place. This approach got us to this place. So that means these two things must be equal. And that's what our rule tells us, that these two things are equal. Okay, try these in your notebook. And after that, you should have a very good review, a very good understanding of laws of exponents. This is something you've done in the past, but maybe this takes you a little further than you've gone before. These rules are very, very important when proceeding with our logarithms unit, so make sure you practice these and understand what's happened. You can do it. Let's check our work. So there's the first 6. And there's the last few of that problem set. All right, hope you had some success with those. This is, again, really good review. Index laws are kind of key to a lot of math and algebraic math you're going to do from here on. With that, you can try these few on the page. There's a few more just to check how you're doing and check the answers as we go here. So here's the first 4. All right, here's the answers to these. Hope they went all right. And a few more on the page that you're taking notes on. These last 3 here. All right, when you're ready, check your work. There's that. Okay, so that's a big lesson. Lots of stuff you did there. But again, brushing up on skills of exponents was a key here. So hope you had some success. If you want, you can tackle this one. Yes, you're welcome. That's a good problem. Lots going on there. Not so bad if you try it out. If you don't have the energy left, don't worry. We'll take a look at that one next time we meet as well. Good work.